Okay, guys. Let's see. Okay. Okay, today, good afternoon, everyone. Today, just want to talk a little bit about functions. Yep, hi. Okay. We'll see them a lot, and we, see functions all the time in many math classes. Okay. Let me remind you what a function is. Wait, this is math. 3274. Just remember, what does it mean to be a function? Well, you have a binary relation. Such that for all A, B1, and B2, if AB1 is in F, AB2 is in F, then B1 equals B2. Okay. Okay, so functions are just sets of ordered pairs satisfying this, well, we could call it the vertical line test or something. Although most functions, it doesn't really make sense to call it the vertical line test for most functions, but anyways, that's just to remind you of what it is. Okay. So like as an example, as a quick example, we could do like set of ordered pairs of real numbers, such that x squared plus y squared equals 1. I guess you could, this is called the unit circle, we call it S1 maybe. Okay, this is not a function. Right, just because, let's say 0, 1 and 0, -1 are in S1, but 1 is not the same as -1. But we can fix it we can define f to be the xy's in R2, such that x squared plus y squared equals 1, and y is greater than or equal to 0. Then we do get a function. This is a function. Okay. But remembering that the domain of the function is just all the, like, comes from the first coordinates of every element of f. We can compute the domain. The domain of f is just all the x's between -1 and 1. Or in other words, the interval -1 to 1. The real number is x such that -1 less than or equal to x less than or equal to 1. Okay. Oh, just a moment. Okay, sorry for that interruption. Yeah, okay, so we see this f is a function, you know, but its domain is just this interval, all the real numbers from -1 to 1. Okay, and to write out, like, to have notation for that, we might write like f goes from -1 to 1 to, you could put a lot of different things for the codomain. We could just put from -1 to 1, the interval 0, 1. And so this notation means that the domain is this set, all the real numbers from -1 to 1. And this notation means that the range of f is a subset of this set, in this case, an interval. Okay. Okay. So, you know, there's a lot of things we usually want to do with functions. But one is to take two functions and see if they're equal or not. Okay, so we have this proposition. That FG be functions. And F equals G if and only if, well, functions that are equal have the same domain. So that's our first thing. The domain of F equals the domain of G. 2, f of x equals g of x for all x in the domain of f. And since domain of f and g are equal, we can put domain of g here. Okay, so this gives us, oh, you didn't see the last line properly. Sorry about that. I'll just, okay, I'm finished writing this proposition. I'll just flip back. The last line on the previous page just says that, so f goes from this interval -1 to 1 and maps it to the interval 0, 1. Okay. Okay, no problem. Going back now. Okay, so we have two functions. We want to know if they're equal. Well, this is what we would normally do, except we would just, you know, in another class, you would say, of course, you all know how to test if two functions are equal, and then we'd say this. Well, now we have to prove something. Okay. Right. So we have two things to prove. But if f equals g, then these 1 and 2 are clear. Because if f equals g, then I just replace all the f's with g's. And this says domain of g equals domain of g, and this says g of x equals g of x. So this is all fine. Okay, so I'll just say forward direction is clear, and that's not supposed to be a trick. If I go through and replace all the f's and if I replace all the s with g's, these two statements are just kind of tautologies, meaning they're just like domain of g equals domain of g and g of x equals g of x. Okay, so this is fine. So there's really only one thing to prove, that if I have two functions satisfying 1 and 2, then f equals g. Okay, so backwards arrow. Assume f and g are functions. And let's assume that the domain of f equals the domain of g. And let's just call this a set A. Okay, we give it the name A. Okay. And now assume for all x in A, f of x equals g of x. And what this means, we have to translate what this means. Okay. Well, we just remember f of x equals y. That just means that xy is an element of f. And because of our definition of function, if x is given, there's only at most one possible y that can satisfy this property. Okay. So let x be an A. So our goal now is to show that, Our goal is to show that these two sets of ordered pairs are equal, right? So let's take an ordered pair in F, and we have to show it's an element of G. Then, by definition of domain, X is in the domain. Because the domain of F is just a set of all things which occur as the first coordinate of something in F. Okay, so X is in the domain of F. Okay, that means that by the definition of f of x, it just means that f of x equals y. Okay. But x is also in the domain of G. And that's because the domain of G equals domain of F, which is which we call A. Okay. So this means that g of y, I'll say, g of x makes sense. And also our assumption is that f of x equals g of x. So g of x equals f of x, and f of x equals y, so we have a y. Okay, therefore you can say that g of x equals y, and that is just another way to say that x comma y is in G. Okay, so we have shown that if xy is in F, then xy is in G. Okay. But the same argument works to show that if xy is in G, then we can show that xy is in F. Okay. So what we can say is we have shown that xy is in F implies xy is in G. The same and the same argument shows that if xy is in G, then xy is in F. But our assumption is that F and G are binary functions. So the only possible elements of F and G are of this form. Okay. But now, let's say if alpha is in F, then F is a function. So alpha is an ordered pair. Oops, for some xy. So because all the elements of F are ordered pairs, and because we've shown that every ordered pair of F is an element of G, so that tells us that all the elements of F are elements of G, and all the elements of G are elements of F. So therefore, we can say that F is a subset of G, and G is a subset of F. So F equals G, and if you want, this is by the axiom of extension, but normally I wouldn't say that, but you know, we can say by axiom of extension. Okay. And that's the end of the proof. So the definition of a function says that two functions are, well, like it says that all functions are just sets satisfying some property. So two functions are equal if they're the same set. But now we kind of have a more useful test to see if two functions are equal. They're equal if they have the same domain, and if f of x equals g of x for all the x in the domain. And that is normally how we would prove that two functions are equal. You know? Okay. So that's the end of the proof there for that proposition. Okay. So we can say now we have a way to test if two functions are equal. Okay, let's talk about composition. Well, actually, we've already defined the composition of two relations. So let's just recall what that is. Recall what is S composed with R. It's all the xz's such that xy is in R and yz is in S for some y. So this lets us compose any two relations. Okay, functions are a special type of relation, so we can compose any two functions. So we have a proposition, which should be kind of surprising at first. Okay. So I guess here I want to ask you guys a question. Is this surprising to you? Okay, that's a good answer. It's not surprising. Yeah, I mean, composition, that's a pretty normal thing. So I want to give you an example to see. Yeah, I want to do a quick example. Okay, and then we'll go back to the proof of the proposition. Okay, the example is, let's take F to be the order pairs, let's say like X, sine X, where X is any real number. In other words, F is a function from R to R given by F of X equals sine X. And then maybe G is going to be the order pairs X, natural logarithm of X, where X is a real number and X is greater than 0. Okay. Now, so this is like equals, this is like the natural logarithm function. So g of x equals natural logarithm of x. The g goes from the positive integers to r. Okay. And now the proposition says that g of f is a function. And what is g of f? It's a set of ordered pairs x natural logarithm of sine of x when there's some sine of x, like when there's some value y, which occurs as the second coordinate in f and simultaneously as the first coordinate in g. So for that to happen, the y has to be positive, right? So it has to be all the real numbers x such that the sine of x is greater than 0. If you want, that's like, if you look at the graph of sine, I guess that should be like x is in the interval from 0 to pi, union 2 pi to 3 pi, and so on, and go on backwards like that. Okay. Okay, so this example should just show you that it's fine that g of f is always a function, but the domain might be weird or something. Okay. So normally when you define composition, like you might have to say something like provided the range of f is contained in the domain of G. Okay, here we don't care. It's fine if the range is not contained in the domain. We still get a function. It's fine. Okay. So we've kind of like relaxed on what is a function and how to compose functions. Right. Proposition. I should also put in a note about what g of f is. G of f is a function, and g of f of x is just g of f of x for all x such that, right, such that x is in the domain of f and f of x is in the domain of G. Okay. And now, you know, just using the composition, this definition of composition, we see that we get the normal, like what would be the normal definition of composition, which is just that g of f of x is just g of f of x. Okay. And this is the usual thing we want. So if I can't write this proposition, then I have no business defining like this symbol. Okay, so let us take like a 3-minute break and just sign back on and do that whole routine. Okay.